Hello friends, with this lecture we start the second part of Econometrics course. This part is mostly devoted to such cases when multiple regression model doesn't work, when the assumptions made don't work. And this lecture is the introduction into the topic about the regression with panel data. Before we start the discussion of the panel data, let's try to remember the most essential things from the first part of this course. We start with the two types of questions we have covered during the first part of the course. We know that one question that we want to answer is to quantify the causal effects when we want to know how much the intervention, some policy action, or some managerial decision might affect the value of interest. Another type of question that we are looking for is to make predictions. In predictions, we don't care about the causality, we don't care about whether there is some influence of one variable to the other. We just want to predict as precise as possible the variable of interest. At this moment, we are familiar to the multiple regression model. We know linear model, we know how to build nonlinear models, and we know OLS estimators that are used to estimate and make inference for the parameters of the multiple regression model. And the most important assumption, not testable assumption, is that the error term in the multiple regression model has a conditional mean independence. We need to remember this since the first half of this course is going to be the discussion of methods when this conditional mean independence assumption fails. Suppose we have a model, linear multiple regression model, where we have several variables of interest, x1, x2, etc., xk, and several control variables, w1, w2, up to wr, and the error term ui. What is the error term? The error term is the effect on y of the variables other than included variables, or we call those other variables omitted variables. We know that once this omitted variable is first a determinant of the dependent variable, and second is correlated with one of the regressors, then OLS estimators of the causal effects are going to be biased. When we make predictions, it is not a large problem because we don't care about quantification of causal effects. But once we want to know to some degree of certainty what is the quantitative estimate of the causal effect, bias is a problem. And well, conditional mean independence assumes this is assumption. This is not a testable assumption, and the only strict way to, let's say, confirm that this assumption holds is to run randomized control experiments. But as we know, working with the observational data prevents us from conducting the experiments. In many cases, in macroeconomics, in microeconomics, we simply are not able to run such experiments. Well, once we control for all variables that are correlated with variables of interest, with x's, and can influence y, we can treat x's as if they were randomly assigned. But the question is, and we stopped here in the first part of the course. Now the question is, what if some of these variables are not observable? What if they are not measurable? Or maybe we simply are not that smart and we forgot or overlooked some of such variables. In this case, of course, the omitted variable bias problem arises, and we cannot claim that the estimated effects with the help of OLS correctly quantify the causal effects. For some specific factors, it is possible to overcome this problem with the help of the panel data. And that's why we start our discussion of the panel data. This is a particular way how we can eliminate the problem of omitted variable bias. So let's start with the terminology. What is the panel data? What are the characteristics of the panel data? So a panel data set contains observations on multiple entities. Might be individuals, firms, states, districts, any other entities, and each entity is observed in the time dimension. So we have 2 or more points in time. For example, we can observe the data on the population in 85 Russian regions for the last 10 years. So every region is a single entity, and for each single entity we observe one variable, which is the population, over 10 years. We introduce this time dimension to the data. Or another example, we can collect the data on consumption spending of 10,000 individuals for 12 months. Every entity is a single individual, and for every single individual we collect the data on the consumption for every month from the 1st to the 12th. Data on revenue of 1,000 firms for the last 5 years. Same idea. Sometimes you can see a term longitudinal data, which is the same as the panel data. We call a balanced panel such panel when there are no missing observations. So every entity has the complete set of observations over time. For every year, we observe all entities in the data. If we have at least one missing observation, we call such panel unbalanced panel. There are specific methods for working with the unbalanced panel. Usually if the number of missing data is not that large, we simply drop such observations. If the data is sparse, there are some other methods to deal with that, but this is not included in our course. So here we can see an example of the panel data and how it is structured in the table format. So we usually start with entities, and here we have entity which is a state, and the next column goes year. And you see that we have 1, 2, 3 up to 7 observations for the same state, for the same entity, but for the different year. So every row in this table now represents entity time observation. So in our case, state year observation. And then we have a lot of variables collected on this state year observation. For example, we have employment, we have beer tax, which is one of the variables we are going to use for our empirical example, we have unemployment rate, we have the spirit consumptions, and some other relevant variables. When we collect the data on all years for one entity, we move to the other entity. In our case, this is the state number 4, and we repeat the collection of these variables for the same time periods from 82 to 88. You're gonna see that, for example, for state 1, beer tax is relatively high. For the other state here, the numbers differ up to 3 times. So the question that we are gonna study in this and the next lecture is how effective are the government policies designed to discourage drunk driving in reducing traffic deaths? So the hypothesis is that once government increases beer tax, it is possible to reduce consumption of alcohol first, and it is possible through this to reduce the traffic deaths. Let's move to the notational part. For the panel data, we introduce a specific notation. And in this specific notation, we have a double subscript that distinguishes entities and time periods. So entity is usually denoted with the letter I. Overall, we have n entities. This is familiar from the previous part of this course, from the cross-sectional data. And now we introduce the time dimension. Time subscript is denoted with small t. This is the time period, and capital T represents the overall number of time periods. So small t starts from 1 and takes values up to capital T. So the data is, if we have only 2 variables, the data is the vector of 2 variables, x, I, t, so for entity I at the period t, and y, I, t. If we have the panel data with k regressors, as we had in the example before, then we have k regressors, x1, x2, xk. All of them must have the same subscript, it, and the dependent variable yit. So why we want to use panel data, why cross-sectional data is not enough. With the help of panel data, we can control for factors that have the following characteristics. So they vary across entities, so they are different for different entities, for example, for states, but they do not vary over time. We will talk a little bit more about such factors related to our example a bit later. Second, of course, we want to control for such factors that can cause omitted variable bias if they are omitted. Because if those factors are not correlated with the included regressors, or if they are not related to the outcome variable, we simply don't care about them. So we do care about such variables that are omitted and that are correlated with the included regressors. And what is the most important, we are not able to measure or observe such variables, because if we are able to do that, well, we simply include those regressors in our model. So the key idea of working with the panel data is, if this omitted variable does not change over time, so this is important, they must be variable over entities, but they allegedly do not vary over time. If this omitted variable does not change over time, then any change in the dependent variable y is not caused by this variable, cannot be caused by this variable, because this variable doesn't change. Based on this idea, we will establish the method how panel data can help us to overcome the problem of omitted variables. So in our example, when we talk about the dataset, traffic death, and alcohol taxes, observational unit is the United States state. I in year T, we have 48 states, we have 7 years, and the panel is balanced. We have the full set of observations for 7 years over 48 states. And the variables that we are going to use to start with are, we collect the data on the traffic fatality rate, which is the number of traffic deaths in state I in year T per 10,000 state residents, and the tax on a case of a beer. We measure this in constant $98 in state I in year T. In addition, we have other variables that might be relevant to estimate the causal effects of a beer tax on the driving and fatality rate. We don't know how to work with the time dimension yet. Therefore, let's try a simple exercise. Let's take a particular year. Let's take a cross-section of 48 states, and let's try to estimate the regression line parameters for the model where fatality rate is regressed on the beer tax in 1982. So here we have the output from Python, and we see that the estimated regression line is the following. So we have an intercept of 2.01, which is statistically significant with p-value less than 5%, and also we have the slope 0.15 positive with the standard error 0.13 and p-value almost 25%. What does this mean? What this result suggests? Well, first of all, the estimate of the slope is not statistically significant, which means that it is highly likely that there is no effect of a beer tax on the fatality rate. And this is interesting that we have a positive estimate. So we might expect a negative sign here because we can logically expect that the higher the taxes are, the less is the consumption of beer, and therefore the less is the fatality rate in car accidents. Let's do the same exercise for another year, 1988. We estimate the regression line, we get the following results, and now, surprise, we have statistically significant estimate of a beer tax, of a slope of a beer tax, and this statistically significant estimate is positive. So here we can observe the scatter plots. The higher the beer tax is, well, there is a slight increase in fatality rate. We can drop these outliers. Maybe there's even no effect without outliers. So for 1988, we see that the result is somewhat stronger. And now this is significantly different from zero. In both cases, we have a positive slope. Well, we might suggest that potentially there is a positive, and there is a positive effect. What is going to be the policy implication? Well, let's drop beer taxes to zero because it will provide us the lowest possible fatality rate from car accidents. Does it seem logical? I don't think so. So, literally higher beer taxes are associated with more and not fewer traffic fatalities. But we didn't expect that. Well, and this result is the example of an omitted variable bias, such severe bias when we even have the switch from expected sign to the opposite sign. What are the potentially missed omitted variables here? For example, quality of automobiles, quality of roads, culture around drinking and driving, density of cars on the road. Some of these variables, for example, culture, is simply not possible to observe and measure. Well, how would we do it? Quality of roads. Well, to some extent it is possible, but also highly problematic to measure quality of roads in each state in every year. And of course, since we omitted these factors that are potentially correlated, that can potentially influence the fatality rate, and maybe some of them are correlated with beer taxes, well, we might expect that there is an omitted variable bias and the estimated effect is simply wrong. So let's start first to remember deeper what is the omitted variable bias and how this omitted variable bias arises. This bias occurs when we omit a factor that is first correlated with one of the included regressors, and second, it is a determinant of the variable of interest. So the omitted variable or the omitted factor, let's denote it z, must be a determinant of y, so this beta 2 must not be 0. This beta 2 is the beta from the true population model. And the second condition for omitted variable bias to appear is that this omitted factor must be correlated with the regressor. You can watch the relevant lecture from the first part if you want to remember more about the omitted variable bias. Well, and both conditions hold for the omission of z, then the result is omitted variable bias. Let's go through some examples of the potentially omitted factors and let's think whether they cause this problem. Traffic density in states. So suppose high traffic density means more traffic death, which seems logical. So x2 is a determinant of y. Some states, like Western states with lower traffic density, have lower alcohol taxes. So this omitted factor is correlated with the included factor. So in this case, we may expect positive bias. Exactly what we have, right? So the positive bias, which shifts our estimate from the negative to the positive number. Example number 2, cultural attitudes towards drinking and driving. Well, we can argue that this is a determinant of traffic death. If for some people in local community it is okay to drink and drive, well, probably we can expect higher number of traffic deaths because of drinking. And potentially this might be correlated with the beer tax, because beer taxes could pick up somehow cultural differences, maybe in such societies where this is not appropriate to drink and drive, maybe taxes are higher. Again, we may expect a positive bias. So can we include these omitted factors into multiple regression? How should we measure them? It's simply not possible. And panel data here is able to help. We are able to eliminate the factors like the ones we have listed here. Let's start with the simple case of a panel data when we have only 2 time periods. Let's consider the following model. So we have a fatality rate, and fatality rate depends on BRICS and depends on the omitted factor Z, which, be careful here, it is not a typo, which is different across entities, but which is constant over time, so it doesn't change over time. For example, cultural differences. It is very difficult to change cultural attitudes, cultural differences over the short period of time. So we can treat that cultural differences over 7 years are approximately constant. The same about quality of roads. Well, sometimes you can significantly improve the quality of roads, but still usually takes a long time to make such improvements. Well, that is a factor that doesn't change over time, at least during the years on which we have data. We need to tell a story, convincing story, that these factors do not change over time. Suppose we don't observe this z, and so if we simply drop this from our model, this result can be the omitted variable bias. But we can eliminate this problem with the help of only 2 years. How? The idea is that if there is a change in the outcome variable in fatality rate between these 2 periods, 82 and 88, since we assume that unobservable factor is constant over time, it doesn't change, then it is not possible that this factor influences a change in the outcome variable, right? So we consider 2 time periods, 82, 88, the model for these 2 time periods, and we see that this element is the same for both equations. We can subtract the first from the second. And that's what we are gonna do. First of all, we assume that once we consider this model, the conditional mean independence assumption holds. And then when we take the differences, we will get the following regression model. We have a change in fatality rate here, and we have a change in the BRICS here. A new error term is not correlated with either BRICS in 88 or BRICS in 82. It is simple to show. And well, we have a usual regression without intercepts. Well, this difference equation can be estimated by OLS, and now the omitted factor does not influence our regression. So it cannot be determinant of a change in y. And now, once we estimate this model, we obtain the following results. Now, the intercept is nearly 0 and not statistically significant, but we don't care about the intercept. What is more interesting is the estimate of slope. Slope now is statistically significant at even 1% level, and the estimate is negative. So now if I change BRICS in a way that the BRICS increases, it must translate into the decrease in fatality rate. The result that we have expected. This is a scatter plot when we regress change in fatality rate on the change in BRICS. The estimated effect is negative. It is statistically significant, and we can Conclude with the help of this estimate that increasing the real bird tax by $1 per case reduces the traffic fatality rate by 1.04 per 10,000 people. Now let's think practically, is this large effect or not? So the average fatality rate is approximately 2. Now, simply increasing tax by $1 will reduce traffic death by half, which is very large effect related to the data. So this is a simple illustration how we can apply the benefits of panel data and the richness of panel data in order to overcome the problem of omitted variable bias in the case when these variables are simply unobservable or unmeasurable. So to conclude this first part of our panel data discussion, let's say that the potential extension of this idea is, what if we have multiple time periods? Like in our data we have 7 periods. Now we worked only with 2 years. What do we have 7? This is one potential development of our model. Another potential development, can we leverage on the fact that we have multiple entities? And the answer is yes. We also can somehow implement the time dimension of our data in a smart way. So next time we will talk about fixed effects regression model, which is now a popular workhorse model once we have panel data and once we want to conduct the econometric research. So let me conclude this lecture at this moment and see you next week. Bye bye.